So how do you estimate for the population mean when you're sampling from a population where you don't know the variance sigma squared? One of the things you're going to have to do is at the same time provide an estimate for sigma. And when you estimate a secondary quantity, in order to be able to estimate the quantity of interest, you are reducing the number of degrees of freedom. And that means that something should be different. There's got to be some way to reflect the fact that you're not using sigma, you're going to be using instead the sample variance, or in this case, the sample standard deviation. So you can still estimate the standard deviation using the sample variance. We have this function here for the sample variance. It requires you to have estimated the sample mean first. Remember, you're dividing by n-1 because you've lost 1 degree of freedom when you estimated the sample mean. And once you have the sample variance, then you can compute the sample standard deviation, which is meant to be an estimate. If you know the true standard deviation, you know from the central limit theorem that the standardization sample mean minus mu divided by standard deviation divided by square root of n is approximately standard normal. If you do not know the standard deviation, if you replace sigma by s, you can still look at the standardization x bar minus mu divided by s divided by square root of n, but now that isn't going to follow a standard normal distribution anymore, or not even approximately. It follows instead a student t distribution with n-1 degrees of freedom. And that's the only difference. You have a different distribution for this quantity, which means that when you compute the confidence intervals, you have to use a different expression here. If you knew sigma, this would be minus z alpha 2, this would be z alpha 2. There wouldn't be a reference to the number of degrees of freedom. But because we're not in the case where we do know sigma, instead, the critical values, the percentiles that we're using are percentiles of the n-1 distribution, the student t distribution with n-1 degrees of freedom. So you have still a curve that looks like this. This is the t n-1 distribution. So you're going to be finding the point minus t alpha 2 n-1. And here you'll have t alpha 2 n-1, for which the area in here is about the same as 1 minus alpha. It means that your tail areas would be alpha over 2. So when you want to build a 95% confidence interval, alpha is equal to 5%. So this area here would be 95%. These areas would be 2.5% each. And you're computing the probability that this quantity that you've computed from your sample would fall somewhere between these 2 points. That should be the area under the curve. Now you can solve for mu in here, multiplying both sides of the inequality by s divided by square root of n, and then sending the x bar to the other side, and you will get that your 100% times 1 minus alpha confidence interval for the mean of the underlying distribution when you do not know the true standard deviation is given by the sample mean plus or minus critical value of the student t distribution with n-1 degrees of freedom at alpha divided by 2 times the sample standard deviation divided by square root of n. And one of the things we've seen is that when n increases, when the sample size gets larger, the student t distribution with n-1 degrees of freedom approaches the standard normal. So if you have a large sample, it doesn't matter that you don't know the true standard deviation. At least it doesn't matter to the same extent. You're getting closer and closer and closer to the case where you can flat out use the central limit theorem with this. Now, how large is large? It depends. It depends on the true underlying distribution. And if the population is normal, rather than just being a population with some distribution, if the population is normal and you do not know the mu and the sigma, this confidence interval is actually an exact confidence interval. So if you're looking for a 95% confidence interval, so your confidence level alpha is 5%, and you have 5 observations in your sample, if you know that these observations come from a normal distribution, for which you do not know the mean, nor do you know the variance, sigma squared, then you need to compute the critical value, 2.5% of the student t distribution with 5 minus 1 degrees of freedom. You go to your table to find that quantity, you will find that it is 2.776. So what this is saying is that on the T4 distribution, the point which will guarantee that this area here is 95% and these other two areas are 2.5% will be 2.776. So that's in your table. And the probability that your standardized quantity here from the sample is actually between these 2 points is 95%. Let's say you have 9 measurements of ozone concentration. 3.5, 5.1, 6.6, 6.0, 4.2, 4.4, 5.3, 5.6, and 4.4. Now, say we have some reason to believe that the ozone concentration measurements follow a normal distribution with a given variance, sigma squared, which is 1.21, which is known. Let's say that I'm asking you to build a 95% confidence interval for the population mean mu. Well, how are you going to do that? Now, I should start by saying that we know that in practice it is impossible for these measurements to be normally distributed. If they were normally distributed, there would be at least the possibility that some of the measurements could be negative. Right? The normal distribution curve has a domain which goes from minus infinity to positive infinity. And so there's a non-zero chance that you would obtain negative numbers. And for measurements of concentration, you cannot get a negative number. But we're going to assume that it does follow a normal distribution, and we assume that we have some reading on the standard deviation of that distribution. Its variance is 1.21. Now, you could compute the sample mean and the sample variance, and of course on a test you'd have to go and compute it, but let's say that this has been done for you. I took these 9 measurements, the sample mean is 5.01, and the sample standard deviation is 0.97. Now you know the variance, so you don't actually need the sample standard deviation. We can use the standard normal percentile, Z alpha divided by 2, because we're building a 95% confidence interval here. This quantity is 1.96. That's one of the ones that we should probably remember, right? So let me just draw this curve again. This is the standard normal. So this is 95%. This point here is 1.96, and this point here is minus 1.96. So because we do know the standard deviation of the underlying normal distribution, we can build a confidence interval. It is simply the sample mean plus or minus Z alpha divided by 2 times the standard deviation divided by the square root of the number of observations. And you plug all of these numbers in, 5.01, 1.96. The true standard deviation is here, so the square root of the variance divided by the square root of the number of observations. And if you work it out, you'll get 5.01 plus or minus 0.72, which is 4.29 to 5.73. What this is telling us is that whenever we sample 9 observations from the population of ozone concentration measurements, we will obtain a confidence interval which will contain the true value mu 95% of the time when we follow this procedure. If we did not know the variance of the underlying population here, we would have to use the sample standard deviation. what you've computed here to be 0.97. And in that case, you cannot use the standard normal to build your confidence interval. You need to use the student t distribution with n-1 degrees of freedom. You're at 95%, so you're looking for the 0.025 critical value. You had 9 observations, so we have 8 degrees of freedom. So you're looking for the value 2.306. Again, you need to make sure you understand how you would extract this value from a student t table of values. Once you have this, you build your confidence interval using the same structure, the difference being that you do not have a standard deviation here. You have a sample standard deviation, which we knew to be 0.97, and you have to use the student t critical value for the alpha and the n that are given in the problem. If you do that, you'll find 5.01. That one hasn't changed. It's the same center. 2.306, that's your critical value. The sample standard deviation is 0.97. It was computed previously, divided by the square root of the sample size, and that gives you 4.26 and 5.76. You'll notice something here. When we do know the variance of the underlying distribution, the confidence interval is tighter, smaller around the sample mean. It's not unexpected that this would be the case. You have more information about the situation, and so you have, technically speaking, more confidence.